Today, let's talk about imperfect multicollinearity. 非完全 or 不完全多重共线性. And in the video later, you will see that first I'll give you the comparison between perfect and imperfect multicollinearity, and then use a regression with only one regressor to show you how the variance of x could affect the standard error of the coefficient of x in the regression. And then use a regression with two regressors to show you how this imperfect multicollinearity affect the variance of x1 or x2, and how would this variance of x1, x2 affect the standard error or variance of b1 and b2. Okay, without further ado, let's get into the class. Let's talk about imperfect multicollinearity. Imperfect multicollinearity. Last time we talked about perfect multicollinearity and also dummy variable trap, which is just an example of perfect multicollinearity. Perfect and imperfect multicollinearity are quite different despite the similarity of the names. Let me give you the comparison. Let me use the regression with two regressors as an example. For perfect multicollinearity, by definition, it says perfect multicollinearity occurs when one regressor is an exact linear function of other regressors. Here we have only two regressors, so you can write this way. x1 is an exact linear function of x2. If this is the case, we say x1, x2 are perfect collinear, or this collinearity is perfect. Okay, perfect multicollinearity. And the intuition behind it is when x2 is held constant and there's nothing changing x1. When x2 is held constant, x1 is also constant. So you cannot estimate the effect of changing x1 on y when x2 is held constant. Right, again, because when x2 is held constant, there's nothing changing x1. Or the data do not contain any information about what happens when x2 changes, but x1 doesn't, or vice versa. Right? But for imperfect multicollinearity, it says this. x1 is still a linear function of x2, but this collinearity is not perfect. Plus error term. They're not perfectly collinear. x1, x2 are not a perfect collinear. So when x2 is held constant, and this part of x1 is constant, but x1 does not only include this component, but also have another component, error term. Right, so you can use x2 to explain some variation in x1, but the rest of the variation in x1 can be explained by some error term. So, or in other words, when x1 and x2 are highly correlated, we say there's imperfect multicollinearity problem. In other words, imperfect multicollinearity occurs when two regressors are very highly correlated. And we call this imperfect multicollinearity. So the logic is pretty much the same. Let's understand the intuition behind this imperfect multicollinearity. So the logic or the intuition behind it is the coefficient on x1, which is measured by b1, right? b1 should give us the effect of changing x1 on y when x2 is held constant. But the thing is, if x1, x2 are highly correlated, there's a very little variation in x1 once x2 is held constant. Right? When x2 is held constant, there's a very little change in x1. If x1, x2 are highly correlated. But for the perfect multicollinearity, when x2 is held constant, there's no change in x1. In perfect multicollinearity, when x2 is held constant, there's very little change in x1. In other words, the data don't contain much information about what happens when x1 changes, but x2 doesn't. Okay, so when there's a perfect multicollinearity, the data do not contain any information about what happens when x1 changes but x2 doesn't. And once you understand this intuition behind it, you can pause this video and think about what will be the consequence or what will be the effect of this imperfect multicollinearity on this OLS estimators, especially B1 and B2. So pause this video and think about it, what effect this imperfect multicollinearity would have on this OLS estimators B1, B2. Before I give you the answer, let me just review this this idea. When the regression only has one regressor, we know we're estimating the regression line, right? So this is a y and this is x. We have scatter plot, number of observations. Suppose n is 100, and let's compare these two situations. Same number of observations, this y and x. We only have one regressor, and then we are estimating a regression line. So this is the variation in x. 100 observations indicate 100 points. And then you can draw the regression line through these points, OLS regression line. Versus you have this 100 observations, you see very little variation in x. And then you draw a regression line based on these 100 observations like this. Which case is better? Or which case will give you a better or more precise estimate? Okay, think about it. Which case will give you a better or more precise estimate of beta 1? Right? Beta 1 is the true effect of changing x on y, or the coefficient of population regression. And we know that B1 is point estimate of beta 1, right? So this is a B1, follow normal distribution, and this is a beta 1. B1 is just an estimate of beta 1. So if the B1 has a very small variation versus this case, this is a B1 and this is a beta 1, but the variation is very large, like this, very large variation. So any point along the x-axis give us the point estimate of beta 1 or a value of B1. So in this case, the variance or standard deviation of B1 is small. In this case, variance or standard deviation of B1 is large. And which one is better? Of course, we know that this one is better. This is the magnitude of B1, but standard error B1 is equally important. We're using standard error B1 to construct confidence interval for beta 1 and also do hypothesis testing, right? Whether beta 1 equals 0. So this is a better case. If this is the case, we say beta 1 is precisely estimated. If this is the case, compare the case above, indicate beta 1 is imprecisely estimated. And which 100 observations can give you a more precisely estimated estimator? This one. In order to have a small standard error of the OLS estimator, B1, we need a large variation in x. So in order for B1 to have a smaller standard error or smaller variance, we need a large variation in this independent variable x. So you can also tell this, you can also see this relationship from the mathematical expression of standard error of B1. Let me show you this. So when you have only one regressor, you have this. Variance of B1 equals 1 over n variance sigma squared of this variable, x minus x bar times error divided by variance of x squared. This is based on regression with one regressor. Okay, you see, when standard deviation of x is large, that means the denominator is large. When denominator is large, a value divided by a large value, right, make variance of B1 smaller, and take a square root. Standard deviation of B1 will become smaller. Right, so the larger the variance of x and the smaller the standard deviation of B1. If the variation in x or variance of x is small, you see the range, or another measure of dispersion. Right, the range of x or dispersion of x or the variance of x is very small, which indicate the denominator is small. Lower denominator, higher variance of B1. Okay, if the B1 has a large variance and the beta 1 is imprecisely estimated. If x has a large variance and denominator is large and variance of B1 will be small, beta 1 is precisely estimated. This is good. Okay, bear this in mind. And then you look at this regression with two regressors. So y equals b0 plus b1 x1 plus b2 x2 and plus error. If there's imperfect multicollinearity, in other words, x1, x2 are highly correlated, are very highly correlated. That means when one variable is held constant, there's very little variation in x1. Very little variation in x1, which will result in a large standard error in B1. So standard error B1 will be large. Same thing. When x1 is held constant, there's very little change in x2. So the result is the standard error of B2 is also large. That is the consequence of imperfect multicollinearity. Okay, imperfect multicollinearity will cause the standard error of the coefficient B1 or standard error of coefficient B2 increase. Okay, again, imperfect multicollinearity results in large standard errors for one or more of the OLS coefficients. If the standard error is large, we say beta 1 is imprecisely estimated, and beta 2 is imprecisely estimated. You see, the imperfect multicollinearity has nothing to do with the magnitude of B0, B1. We know that there are 4 least square assumptions for causal inference, right? No correlation, so conditional means 0, right? Conditional means 0, so that's expected value of error given x1, x2 equals 0, and IID, and no perfect multicollinearity, and no extreme outliers. As long as these 4 least square assumptions are satisfied, B1 will be unbiased, right? Which means expected value B1 equals beta 1. If there's no correlation between x2 and error, once x1 is held constant, there's no bias in B2. Right? That means B2 is also unbiased, has a causal effect. If x1 is our variable interest, these 4 conditions are satisfied, B1 will be unbiased. Right? So you see these 4 least square assumptions for causal inference does not require no imperfect multicollinearity. That means the imperfect multicollinearity will not affect the magnitude or the value of B1, B2. However, it will affect the standard error of B1, B2. In practice, if you run a regression with 2 regressors and then you find B1, B2 are significant, and then you consider add another regressor, X3. When you add this another regressor, X3, all of a sudden all the coefficients become insignificant. And that's a sign of imperfect multicollinearity. Another thing I want to add to this video is, you see I gave you this variance of B1, which is only applied to regression with only 1 regressor. And now if you have regression with 2 regressors and how to calculate or what are the expression for variance or standard error of B1. So let me give you that expression just for your reference. So variance of B1, which is based on regression with 2 regressors, okay, and that equals 1 over n times 1 over rho squared, that's correlation coefficient between x1, x2 squared, times variance of error, variance of x1. That's the mathematical expression for variance of B1 based on regression with the 2 regressors. You see, you have this variance of error that indicate in this case errors are homoscedastic. Okay, so when correlation coefficient between x1 and x2 is large, so 1 minus a large value, denominator is smaller. Lower denominator and enlarge the variance of B1. Again, when x2 is held constant, if x1, x2 are very highly correlated, there is very little change in x1. In other words, variance of x1 is very small, which will cause standard error of B1 to be large, which will increase standard error of B1. when standard error B1 is large and beta 1 is imprecisely estimated. Okay, you're using standard error B1 to estimate the confidence interval for beta 1 and test the hypothesis that beta 1 equals a value, right? So you can easily find your coefficient not statistically significant, right, because of this imperfect multicollinearity. Yeah, I hope you'll find this helpful. I hope you find this video helpful, and to reduce the length of the video, I will talk about the remedy of this problem in the next video. Okay, in the next video, I might talk about the remedy, or what we could do to mitigate the negative effect of imperfect multicollinearity on the regression model. So stay tuned, and I'll see you next time. Bye.